Question 1. Compliance review shows that an automated provisioning script utilizing the OCI command line interface, CLI, has been configured using the tenancy's root user credentials, with these credentials embedded directly within the script's source code. What is the most appropriate remediation strategy to ensure secure and compliant operation of the OCI CLI for this automation? Option A. Create a dedicated OCI IAM service principal with the minimum necessary permissions to perform the script's intended actions, and configure the OCI CLI to use this service principal's credentials securely. Option B. Store the root user's credentials in a secure vault service and update the script to retrieve them from the vault before execution. Option C. Revoke the root user's credentials and grant the OCI CLI broad administrative privileges to all resources within the tenancy via a user group. Option D. Continue using the root user credentials for the OCI CLI, but implement additional network security controls around the server running the script. The correct answer is A. Create a dedicated OCI IAM service principal with the minimum necessary permissions to perform the script's intended actions, and configure the OCI CLI to use this service principal's credentials securely. Explanation. Scenario analysis. This scenario presents a common challenge in cloud environments where automated provisioning and configuration management are critical for maintaining security and compliance. The challenge lies in ensuring that the OCI CLI, a powerful tool for interacting with OCI services, is used in a manner that adheres to established security policies and audit requirements. The need to grant broad access for automation scripts while simultaneously enforcing granular permissions and maintaining an auditable trail is a delicate balance. Misconfigurations can lead to unauthorized access, data breaches, or noncompliance with internal governance and potentially external regulatory frameworks, though for this exam, we focus solely on OCI best practices and implied governance. Correct approach analysis. The correct approach involves leveraging OCI identity and access management (IAM) policies to grant the OCI CLI the least privilege necessary for its intended operation. This means creating a dedicated IAM user or service principal for the CLI, assigning it only the permissions required to manage specific OCI resources, e.g., compute instances, storage buckets, within a defined compartment. Furthermore, using OCI CLI configuration profiles to manage credentials securely, avoiding hard-coding sensitive information, and ensuring that the CLI commands themselves are logged or auditable, are crucial for maintaining a secure and compliant operational posture. This aligns with the principle of least privilege, a fundamental security best practice that minimizes the potential impact of a compromised credential or an accidental misconfiguration. Incorrect approaches analysis. Using the root user's credentials for the OCI CLI is a significant security and compliance failure. Root user has unrestricted access to all resources in the tenancy, violating the principle of least privilege. If these credentials were compromised, the entire tenancy would be at risk. This approach also bypasses granular access controls, making it impossible to audit specific actions taken by the CLI. Granting overly broad permissions to a user account that is also used for interactive management is another failure. While the user might need broad access for their daily tasks, the OCI CLI should operate with a distinct, more restricted set of permissions. This separation of duties is essential for security and auditability. If the user account is compromised, the OCI CLI's broad permissions could be exploited. Storing OCI CLI credentials directly within automation scripts or configuration files in plain text is a critical security vulnerability. This exposes sensitive authentication information, making it easily accessible to anyone who can access the script or file. This directly contravenes secure credential management practices and would be a major audit finding. Professional reasoning. Professionals should approach OCI CLI implementation by first understanding the specific tasks the CLI will perform and the OCI resources it needs to interact with. This understanding should then translate into a meticulously crafted IAM policy that grants only the necessary permissions. Secure credential management, including the use of OCI CLI configuration profiles and avoiding hard-coded secrets, is paramount. Regular auditing of CLI activity and access logs is also a vital component of a robust security posture. The decision-making process should always prioritize security, compliance, and the principle of least privilege. Question 2. The monitoring system demonstrates that several compute instances and block volumes within an Oracle Cloud Infrastructure (OSI) environment are consistently underutilized, showing low CPU and I/O activity over the past quarter. The finance department is pushing for immediate cost reductions. Which of the following strategies would be the most professionally sound and cost-effective in the long term? Option A. Immediately terminate all compute instances and detach all block volumes that show any indication of low utilization to achieve maximum immediate cost savings. Option B. Disable the monitoring and logging services for these underutilized resources to prevent them from incurring further costs. Option C. Increase the size of all compute instances to ensure they can handle any potential future workload, even if current utilization is low. To avoid future scaling costs, Option D. Conduct a detailed analysis of the utilization metrics for each underutilized resource to identify opportunities for right-sizing compute instances, deleting unattached block volumes, and scheduling shutdowns for non-production instances during off-peak hours. The correct answer is D. Conduct a detailed analysis of the utilization metrics for each underutilized resource to identify opportunities for right-sizing compute instances, deleting unattached block volumes, and scheduling shutdowns for non-production instances during off-peak hours. Explanation: this scenario is professionally challenging because it requires balancing immediate cost savings with long-term performance, availability, and adherence to Oracle's best practices for OCI. The architect must consider not only the current expenditure, but also the potential impact on application responsiveness, scalability, and the ability to meet future business demands. A hasty decision based solely on reducing the current bill can lead to significant operational issues and increased costs down the line due to performance degradation or the need for emergency scaling. The correct approach represents best professional practice because it involves a holistic review of resource utilization, performance metrics, and business requirements before implementing changes. This aligns with the principles of responsible cloud resource management, which emphasize efficiency, cost-effectiveness, and sustainability. By analyzing actual usage patterns and identifying underutilized resources, the architect can make informed decisions about right-sizing or decommissioning, thereby optimizing costs without compromising performance. This proactive and data-driven approach minimizes risk and ensures that cloud investments are aligned with business objectives, a key tenet of professional cloud architecture. An incorrect approach that involves immediately terminating all idle resources without proper analysis is professionally unacceptable. This could lead to service disruptions if those resources, though currently idle, are critical for scheduled tasks, backups, or sudden demand spikes. Such an action demonstrates a lack of due diligence and a failure to understand the interconnectedness of cloud services. It also ignores the potential for future, albeit infrequent, legitimate use, leading to the cost of reprovisioning and potential data loss or downtime if not managed carefully. Another incorrect approach, such as disabling monitoring altogether to avoid associated costs, is ethically and professionally unsound. Monitoring is fundamental to security, performance, and cost management. Disabling it creates blind spots, making it impossible to detect security breaches, performance bottlenecks, or further cost inefficiencies, thereby exposing the organization to significant risks. Professionals should employ a decision-making framework that prioritizes understanding the current state through comprehensive monitoring and analysis. This involves gathering data on resource utilization, performance metrics, and cost trends. Next, they should evaluate potential optimization strategies against business requirements, considering factors like performance SLAs, availability needs, and future growth projections. Finally, they should implement changes incrementally, monitor their impact, and iterate as necessary. This systematic approach ensures that cost optimization efforts are effective, sustainable, and do not negatively impact the business. Question 3. System analysis indicates that an organization is deploying a critical application on Oracle Cloud Infrastructure, OSI, that requires secure access to OCI object storage for data backups and OCI autonomous database for transactional data. The application also needs to communicate with other internal OCI services. The architecture must adhere to a secure by default posture, minimizing the attack surface while ensuring application functionality, Which network security configuration best meets these requirements? Option A. Disable all network security controls within the OCI Virtual Cloud Network, VCN, and rely solely on OCI's inherent security features. Option B. Implement security lists and network security groups, NSG, with explicit rules allowing only the necessary ingress and egress traffic to and from object storage and autonomous database on their respective ports and protocols, while denying all other traffic. Option C. Configure broad firewall rules that permit all inbound and outbound traffic to and from all OCI services to ensure no communication is inadvertently blocked. Option D. Create highly restrictive firewall rules that block all traffic by default, and then manually add exceptions for every single IP address that needs to communicate with the application, without considering specific OCI service endpoints. The correct answer is B. Implement security lists and network security groups, NSG, with explicit rules allowing only the necessary ingress and egress traffic to and from object storage and autonomous database on their respective ports and protocols, while denying all other traffic. Explanation. Scenario analysis. This scenario presents a common challenge in cloud environments where organizations must balance robust network security with the operational needs of their applications. The core difficulty lies in implementing granular network access controls that comply with evolving security best practices and potential regulatory mandates. Though specific regulations are not detailed here, the principle of compliance is paramount for an OCI architect associate. The need to restrict access to specific OCI services while allowing necessary communication for application functionality requires a deep understanding of OCI networking constructs and security services. Misconfigurations can lead to either security vulnerabilities or service disruptions, both of which have significant business implications. Correct approach analysis. The correct approach leverages OCI's native network security features, specifically security lists and network security groups, NSG, in conjunction with the principle of least privilege. Security lists operate at the subnet level, providing stateful firewall rules. NSGs offer more granular control, allowing rules to be associated directly with VNIC of compute instances. By defining rules that permit only the necessary ingress and egress traffic to and from specific OCI services, e.g., object storage, autonomous database, on their designated ports and protocols, while denying all other traffic, the architecture adheres to a secure-by-default posture. This approach is best professional practice because it minimizes the attack surface by explicitly allowing only required communication, thereby reducing the risk of unauthorized access or data exfiltration. It aligns with the fundamental security principle of least privilege, ensuring that network resources are only accessible to authorized entities for legitimate purposes. Incorrect approaches analysis. One incorrect approach involves relying solely on broad, permissive firewall rules that allow all inbound and outbound traffic to and from OCI services. This is a significant regulatory and ethical failure because it violates the principle of least privilege and creates a wide-open attack vector. Such a configuration would likely fail any security audit and expose the organization to considerable risk of breaches, potentially leading to non-compliance with data protection regulations and severe reputational damage. Another incorrect approach is to disable all network security controls, assuming that OCI's inherent security is sufficient. This is fundamentally flawed and represents a failure to implement due diligence in securing cloud resources. It ignores the shared responsibility model in cloud security, where the customer is responsible for configuring and managing network security. This approach would be a clear violation of security best practices and could lead to severe compliance issues if specific industry regulations mandate network segmentation and access control. A third incorrect approach might be to implement overly complex and restrictive firewall rules that inadvertently block legitimate application traffic. While the intent is security, the outcome is service disruption. This is professionally challenging because it requires careful testing and validation. From a regulatory perspective, while not directly a violation of a security regulation, it can lead to business continuity failures and potentially impact compliance with service-level agreements, SLAs, or other operational mandates. The failure here is in the execution and testing of the security policy, not necessarily the intent. Professional reasoning. Professionals should approach network security design by first understanding the application's communication requirements. This involves identifying all OCI services the application needs to interact with and the specific ports and protocols required for those interactions. Subsequently, they should apply the principle of least privilege by creating granular firewall rules using security lists and NSGs to permit only this identified traffic. All other traffic should be implicitly denied. Regular review and auditing of these rules are crucial to adapt to changing application needs and evolving security threats. This systematic approach ensures both security and operational integrity, aligning with professional responsibilities and potential regulatory expectations for secure cloud deployments. Question 4. Assessment of the most suitable Oracle Cloud Infrastructure Service model for a new financial reporting application that requires strict data residency controls, custom integration with existing on-premises legacy systems, and a need for granular control over the operating system and network configurations to meet stringent security audit requirements. Option A. Platform as a Service (PaaS). Option B. Software as a Service (SaaS). Option C. Infrastructure as a Service (IaaS). Option D. A hybrid approach combining IaaS and SaaS. The correct answer is C. Infrastructure as a Service (IaaS). Explanation. This scenario presents a common challenge for architects, balancing business agility with robust security and compliance requirements within a cloud environment. The core difficulty lies in selecting the appropriate Oracle Cloud Infrastructure (OCI) service model that aligns with the organization's specific needs for control, customization, and operational overhead, while adhering to the regulatory framework relevant to the Oracle Cloud Infrastructure 2023 Certified Architect Associate exam, which implicitly assumes a general understanding of cloud governance and best practices, without specifying a particular national jurisdiction beyond what OCI itself adheres to. The correct approach represents best professional practice because it prioritizes a thorough understanding of the application's requirements and the organization's capabilities before making a service model decision. This ensures that the chosen model provides the necessary level of control and security without introducing unnecessary complexity or cost. For instance, selecting infrastructure as a service (IaaS) when a platform as a service (PaaS) offering would suffice might lead to increased management overhead and potential security gaps if not meticulously managed. Conversely, opting for a SaaS solution when deep customization or specific integration with on-premises systems is critical could lead to vendor lock-in and unmet business needs. The professional decision-making process involves a systematic evaluation of application architecture, data sensitivity, compliance mandates, and the organization's IT expertise. Incorrect approaches fail by either oversimplifying the decision-making process, leading to potential compliance violations or operational inefficiencies, or by making assumptions that do not align with the principle of least privilege or the shared responsibility model inherent in cloud computing. For example, defaulting to the most managed service, SaaS, without verifying if it meets all functional and data residency requirements could lead to a breach of data privacy regulations or contractual obligations. Similarly, choosing IaaS solely for perceived control without a clear strategy for managing the underlying infrastructure can result in security vulnerabilities and increased operational costs, potentially violating internal governance policies or industry best practices for cloud security. The professional reasoning process should involve a detailed assessment of the application's functional and non-functional requirements, including performance, scalability, security, and compliance. This should be followed by an evaluation of the organization's existing IT capabilities and risk tolerance. Finally, a comparative analysis of OCI's IaaS, PaaS, and SaaS offerings against these requirements and capabilities will guide the selection of the most appropriate service model. This iterative process ensures that the chosen solution is technically sound, operationally feasible, and compliant with relevant governance frameworks. Question 5. Comparative studies suggest that the optimal selection of Oracle Cloud Infrastructure (VM) instance shapes is critical for balancing performance and cost. A company is deploying a new web application that is expected to experience variable traffic patterns, with occasional spikes in user activity. The application is moderately CPU-intensive and requires sufficient memory to cache frequently accessed data. Network latency is a concern for user experience, and the application will store its data in OCI block volume. Which of the following approaches best aligns with professional best practices for selecting an appropriate VM instance shape for this web application? Option A. Select an instance shape from the compute-optimized family that offers the highest number of OCPU, as this will ensure the application can handle any traffic spike. Option B. Prioritize an instance shape from the memory-optimized family to ensure ample caching capacity, even if it means over-provisioning CPU resources. Option C. Choose an instance shape from the general-purpose family that provides a balanced ratio of OCPU to memory, and then monitor performance to adjust if necessary. Option D. Select an instance shape from the dense I/O family to guarantee the fastest possible access to the block volume, as this is the primary storage. The correct answer is A. Select an instance shape from the compute-optimized family that offers the highest number of OCPU, as this will ensure the application can handle any traffic spike. Explanation. Scenario analysis. This scenario presents a common challenge in cloud architecture, selecting the most appropriate VM instance shape for a given workload while balancing performance, cost, and future scalability. The professional challenge lies in understanding the nuanced differences between VM families and shapes, and how these translate to real-world application performance and operational efficiency. Misjudging these factors can lead to overspending on underutilized resources or, conversely, performance bottlenecks that impact user experience and business operations. The need for a cost-effective yet performant solution requires a deep understanding of the OCI service catalog and the specific characteristics of each instance type. Correct approach analysis. The correct approach involves a thorough assessment of the application's specific requirements, including CPU, memory, network, and storage IOPS needs. It then maps these requirements to the most suitable VM instance family and shape. For instance, if the application is CPU-bound and requires high network throughput, an instance family optimized for compute and networking would be prioritized. If the application is memory-intensive, a memory-optimized shape would be the logical choice. This approach represents best professional practice because it is data-driven, aligns resource allocation with actual needs, and promotes cost optimization. It avoids speculative over-provisioning and ensures that the chosen shape can adequately support the application's current and anticipated future demands, thereby maximizing the return on investment in cloud infrastructure. This aligns with general principles of efficient resource management and responsible cloud adoption, which are implicitly expected in professional IT environments. Incorrect approaches analysis. Choosing an instance shape solely based on the highest available core count without considering other resource requirements is professionally unacceptable. This can lead to significant cost overruns if the application does not fully utilize the CPU, or if it is bottlenecked by other resources like memory or network. It demonstrates a lack of understanding of how different VM shapes are optimized for specific workloads and can result in inefficient resource utilization. Selecting an instance shape based on the lowest cost without a proper performance assessment is also professionally unsound. While cost is a critical factor, prioritizing it above all else can lead to severe performance degradation, impacting application responsiveness, user satisfaction, and potentially business revenue. This approach fails to consider the total cost of ownership, which includes the cost of poor performance and potential rework. Opting for a general-purpose instance shape without verifying if it meets the specific performance characteristics of the workload is a common pitfall. While general-purpose shapes offer a good balance, specialized workloads might benefit significantly from compute-optimized, memory-optimized, or GPU-accelerated shapes. Failing to investigate these specialized options can lead to suboptimal performance and missed opportunities for efficiency gains. This approach lacks the due diligence required for effective cloud architecture design. Professional reasoning. Professionals should approach VM instance selection by first understanding the application's workload characteristics. This involves profiling the application to identify its primary resource demands: CPU, memory, network, storage. Next, they should consult the Oracle Cloud Infrastructure documentation to understand the different VM instance families, e.g., AMD, Intel, ARM, and their respective shapes, noting their specific optimizations and performance profiles. A comparative analysis of potential shapes against the identified workload requirements, considering both performance and cost, is crucial. Finally, a phased deployment or testing approach, where possible, can validate the chosen shape before full production rollout, allowing for adjustments based on real-world performance metrics. Question 6. The efficiency study reveals that the organization's data storage practices are suboptimal, leading to increased costs and performance bottlenecks. The company has several distinct data categories: critical operational databases requiring high IOPS and low latency, large volumes of unstructured user-generated content with infrequent but rapid access needs, shared file systems for collaborative development environments, and historical log data that must be retained for compliance but is rarely accessed. Which OCI storage strategy best addresses these diverse requirements while optimizing for cost and performance? Option A. Primarily use object storage infrequent access for all data, assuming that most data will eventually become infrequently accessed. Option B. Deploy block storage for all data categories to ensure consistent high performance across the entire data landscape. Option C. Utilize object storage standard for all data categories, leveraging its scalability and cost-effectiveness for all access patterns. Option D. Implement a multi-tiered storage approach. Block storage for operational databases, object storage standard for user-generated content, file storage for collaborative environments, and archive storage for historical logs. The correct answer is C. Utilize object storage standard for all data categories, leveraging its scalability and cost-effectiveness for all access patterns. Explanation: scenario analysis. This scenario presents a common challenge in cloud architecture where balancing performance, cost, and data durability is critical. The efficiency study highlights a need to optimize storage solutions for different data access patterns and retention requirements. The challenge lies in selecting the most appropriate Oracle Cloud infrastructure, OSI, storage service for each data type, considering not only technical specifications, but also the implicit regulatory and compliance considerations that often accompany data management, even if not explicitly stated as a regulatory framework in the prompt. Professional judgment is required to map data characteristics to OCI service features and understand the implications of each choice on operational efficiency and potential future auditability. Correct approach analysis. The correct approach involves a granular analysis of each data type's characteristics and aligning them with the strengths of OCI's storage services. For frequently accessed, performance-sensitive data, block storage offers high IOPS and low latency, suitable for boot volumes and transactional databases. For unstructured data with varying access needs, object storage provides scalability and cost-effectiveness, with different tiers, standard, infrequent access, archive, to match access frequency and retention policies. File storage is ideal for shared file systems and applications requiring POSIX compliance. Archive storage is the most cost-effective for long-term data retention with infrequent access. This multi-tiered, service-specific approach ensures optimal performance, cost, and compliance with data lifecycle management principles, which are foundational to good governance and operational best practices. Incorrect approach is analysis. An approach that exclusively uses object storage for all data types, regardless of access patterns or performance needs, would be professionally unacceptable. While object storage is versatile, it may not meet the low latency requirements for boot volumes or transactional databases, leading to performance degradation and operational inefficiency. This could indirectly impact compliance with service level agreements, SLAs, if performance is a contractual obligation. Another incorrect approach would be to use block storage for all data, including large volumes of infrequently accessed archival data. This would be prohibitively expensive and inefficient, as block storage is designed for high performance and is priced accordingly. It fails to leverage the cost optimization capabilities of OCI's tiered storage, demonstrating a lack of understanding of service suitability and potentially leading to budget overruns. Finally, an approach that ignores the distinct access patterns and retention requirements, opting for a single, generic storage solution without proper analysis, would be a failure in professional due diligence. This demonstrates a lack of understanding of data lifecycle management and the principle of least privilege and cost optimization, which are core tenets of effective cloud architecture. It could lead to overspending, underperformance, and difficulties in meeting future data governance or compliance needs. Professional reasoning. Professionals should adopt a data-centric approach, understanding that different data has different requirements. The decision-making process should involve 1. classifying data based on access frequency, performance needs, and retention policies. 2. Mapping these classifications to the most suitable OCI storage service, object storage tiers, block storage, file storage, archive storage. 3. Considering cost implications and scalability for each choice. 4. Documenting the rationale for each storage selection to ensure transparency and facilitate future reviews or audits. This systematic approach ensures that the architecture is not only technically sound, but also cost-effective and aligned with business objectives and potential regulatory considerations. Question 7. To address the challenge of ensuring comprehensive visibility into the health, performance, and security of applications deployed on Oracle Cloud Infrastructure Container Engine for Kubernetes Oak, which approach best aligns with OCI's best practices and regulatory considerations for monitoring and logging. Option A. Focus exclusively on monitoring external-facing application performance metrics and ignore internal cluster and pod-level logs and metrics. Option B. Configure OCI monitoring to collect key cluster and pod metrics, and OCI logging to ingest logs from OKE control plane components, worker nodes, and application pods, establishing centralized alerting and analysis capabilities. Option C. Deploy a custom, self-managed logging agent on each worker node and configure it to send logs to an external, non-OCI managed log aggregation service. Option D. Manually aggregate log files from individual worker nodes on a daily basis to review for potential issues. The correct answer is B. Configure OCI monitoring to collect key cluster and pod metrics, and OCI logging to ingest logs from OKE control plane components, worker nodes, and application pods, establishing centralized alerting and analysis capabilities. Explanation. Scenario analysis. This scenario presents a common challenge in cloud environments where maintaining visibility into application behavior and potential security incidents is paramount. The complexity arises from the distributed nature of Kubernetes clusters, the ephemeral characteristics of pods, and the need to correlate events across different services and infrastructure components. Organizations must balance the need for comprehensive monitoring and logging with the operational overhead and cost implications of implementing and managing these solutions. Failure to establish effective monitoring and logging can lead to delayed incident detection, difficulty in root cause analysis, and potential compliance breaches. Correct approach analysis. The correct approach leverages OCI's native monitoring and logging services, specifically OCI monitoring and OCI logging, integrated with OCI Container Engine for Kubernetes Oak. This approach represents best professional practice because it aligns with the principle of using integrated, cloud-native solutions for enhanced efficiency and reduced complexity. OCI monitoring allows for the collection and alerting on key metrics from OKE clusters, such as pod health, resource utilization, and API server performance. OCI logging provides a centralized platform for collecting logs from pods, nodes, and control plane components, enabling detailed analysis and troubleshooting. By configuring these services to ingest OKE logs and metrics, architects can establish a robust observability posture. This is crucial for meeting potential regulatory requirements related to audit trails and incident response, ensuring that critical events are captured and can be investigated promptly. The integration ensures that data is readily available for security analysis and operational troubleshooting without requiring extensive custom integrations or third-party tools, which can introduce additional security risks and management burdens. Incorrect approaches analysis. One incorrect approach involves relying solely on manual log file aggregation from individual worker nodes. This is professionally unacceptable because it is highly inefficient, prone to errors, and fails to provide a centralized, real-time view of the cluster's health. It creates significant blind spots, making it impossible to effectively monitor the overall state of the OKE cluster, or to detect and respond to incidents in a timely manner. From a regulatory perspective, this approach would likely fail to meet requirements for comprehensive audit trails and demonstrable security monitoring capabilities. Another incorrect approach is to implement a custom logging solution using open-source tools without proper integration with OCI's native services. While open-source tools can be powerful, a purely custom, unmanaged solution can introduce significant security vulnerabilities if not meticulously maintained and secured. It also bypasses the benefits of OCI's managed services, leading to increased operational overhead for patching, scaling, and ensuring data durability. This can also create challenges in meeting compliance standards that often expect the use of established, well-supported platforms for critical functions like logging and monitoring. A further incorrect approach is to only monitor external-facing application metrics and ignore internal cluster and pod-level logs and metrics. This is professionally unsound as it provides an incomplete picture of system health and security. Critical issues within the cluster, such as pod crashes, resource starvation, or internal service communication failures, would go undetected. This lack of deep visibility hinders effective troubleshooting and incident response, potentially leading to prolonged outages and security breaches that could have been mitigated with comprehensive monitoring. It also fails to provide the necessary granular data for forensic analysis required by many regulatory frameworks. Professional reasoning. Professionals should approach monitoring and logging for OKE by first understanding the specific observability requirements driven by application criticality, security policies, and potential regulatory obligations. The decision-making process should prioritize leveraging cloud-native services for their integration, scalability, and managed nature. Architects should then design a solution that captures both metrics and logs from all relevant components, including the OKE control plane, worker nodes, and deployed applications. This involves configuring OCI monitoring for alerting on key performance indicators and potential anomalies, and OCI logging for the collection, retention, and analysis of logs. Regular review and refinement of monitoring dashboards and alerting rules are essential to adapt to evolving application needs and threat landscapes. Question 8. The control framework reveals an urgent requirement to deploy a new microservices-based application on Oracle Cloud infrastructure within a tight deadline. The development team has containerized the application and is requesting a Kubernetes environment. The cloud architect is considering different approaches to provision and manage this Kubernetes cluster, balancing speed of deployment with security and operational best practices. Which approach best aligns with the principles of secure and efficient cloud architecture within OCI? Option A. Manually set up a self-hosted Kubernetes cluster on OCI compute instances, managing all control plane components and worker nodes independently. Option B. Provision a managed Oracle container engine for Kubernetes Oak cluster, configuring network security and IAM policies according to OCI best practices and organizational security guidelines. Option C. Deploy the containerized application directly onto OCI compute instances without using a container orchestration platform. Option D. Utilize a third-party Kubernetes distribution installed on OCI compute instances without specific integration with OCI's native security and networking services. The correct answer is B. Provision a managed Oracle container engine for Kubernetes Oak cluster, configuring network security and IAM policies according to OCI best practices and organizational security guidelines. Explanation. Scenario analysis. This scenario presents a professional challenge where a cloud architect must balance the immediate need for rapid deployment with the imperative of adhering to established security and operational best practices within the Oracle Cloud Infrastructure (OCI) environment. The pressure to deliver quickly can lead to shortcuts that compromise long-term stability, security, and compliance. The architect's judgment is critical in navigating these competing demands, ensuring that technical decisions align with organizational policies and regulatory requirements, even under time constraints. Correct approach analysis. The correct approach involves leveraging OCI's managed Kubernetes service, Oracle Container Engine for Kubernetes Oak, and its integrated security features. This aligns with best professional practice because OCI's managed services are designed to abstract away much of the underlying infrastructure complexity, including the control plane management, patching, and security hardening. By using OKE, the architect ensures that the Kubernetes cluster is provisioned and maintained according to OCI's security standards and best practices, which are informed by industry regulations and compliance frameworks relevant to cloud services. This approach minimizes the risk of misconfiguration, reduces the operational burden on the team, and provides a more secure and stable foundation for containerized applications. It also facilitates easier integration with other OCI security services like Identity and Access Management (IAM) and Virtual Cloud Network (VCN), Security lists, ensuring a holistic security posture. Incorrect approach is analysis. One incorrect approach involves manually provisioning and managing a self-hosted Kubernetes cluster on OCI compute instances without utilizing OKE. This is professionally unacceptable because it bypasses OCI's built-in security controls and best practices for Kubernetes management. The architect would be solely responsible for securing the control plane, managing ET, implementing network policies, and ensuring regular patching and updates, which is a complex and error-prone task. This significantly increases the risk of security vulnerabilities and operational instability, potentially leading to compliance failures if the self-managed cluster does not meet required security baselines. Another incorrect approach is to deploy applications directly onto OCI compute instances without containerization or orchestration. This fails to leverage the benefits of Kubernetes for scalability, resilience, and efficient resource utilization. From a control framework perspective, it makes it harder to enforce consistent security policies, manage application lifecycles, and audit deployments, which are key aspects of a robust cloud governance model. It also deviates from modern cloud-native architectural patterns that are often expected for efficiency and agility. A third incorrect approach is to deploy applications using a third-party Kubernetes distribution on OCI compute instances without proper integration with OCI's native security and networking services. While third-party distributions can be powerful, their integration with the cloud provider's security fabric is crucial. Failing to properly integrate can lead to security gaps, such as unmanaged network traffic, inconsistent identity and access controls, and difficulty in monitoring and logging, all of which can result in regulatory noncompliance and operational risks. Professional reasoning. Professionals should adopt a decision-making process that prioritizes leveraging managed services for core infrastructure components like Kubernetes. This involves understanding the capabilities and security features offered by the cloud provider, OCI in this case, and aligning them with organizational requirements and regulatory obligations. When faced with time pressure, the focus should be on efficient and secure implementation, not on cutting corners that introduce long-term risks. A thorough assessment of the trade-offs between self-management and managed services, considering security, operational overhead, and compliance is essential. The principle of least privilege and defense in depth should guide all architectural decisions, ensuring that security is built in from the start. Question 9. The risk matrix shows a high likelihood of unauthorized data access and a moderate impact from data exfiltration for a new customer-facing application deployed on Oracle Cloud infrastructure. The development team is pushing for a rapid deployment timeline to meet market demand. What is the most appropriate architectural approach to mitigate these risks while enabling timely deployment? Option A. Deploy the application with minimal security configurations to expedite the launch, with plans to address security enhancements post-deployment. Option B. Implement granular access controls using OCI Identity and Access Management (IAM) policies, secure sensitive data with OCI Vault for key management and encryption, and enforce network segmentation with OCI Network Security Groups (NSG) for compute instances. Option C. Rely on the default security settings provided by OCI services, assuming they are sufficient for a new application. Option D. Utilize third-party security tools that offer quick integration, without a thorough review of their compliance certifications or OCI compatibility. The correct answer is B. Implement granular access controls using OCI Identity and Access Management (IAM) policies, secure sensitive data with OCI Vault for key management and encryption, and enforce network segmentation with OCI Network Security Groups (NSG) for compute instances. Explanation. Scenario analysis. This scenario presents a common challenge in cloud adoption, balancing the need for rapid deployment and innovation with robust security and compliance requirements. The pressure to deliver new features quickly can lead to shortcuts that expose sensitive data or violate regulatory mandates. The architect must navigate these competing priorities, ensuring that the chosen OCI services and configurations meet both business objectives and the stringent requirements of the Oracle Cloud Infrastructure 2023 Certified Architect Associate Syllabus, which implicitly assumes adherence to common cloud security best practices, and by extension, relevant data protection regulations applicable to cloud services. The professional challenge lies in translating abstract risk assessments into concrete, actionable architectural decisions that are both effective and compliant. Correct approach analysis. The correct approach involves a thorough understanding of OCI's security services and their integration capabilities, specifically leveraging OCI Identity and Access Management (IAM) for granular control over resource access, OCI Vault for secure management of secrets and encryption keys, and OCI Network Security Groups (NSG) to define ingress and egress traffic rules for compute instances are fundamental. This approach directly addresses the identified risks by implementing layered security controls. The use of IAM ensures that only authorized personnel and services can access sensitive data, aligning with principles of least privilege. OCI Vault provides a centralized and secure method for managing sensitive credentials and keys, crucial for data encryption at rest and in transit, thereby meeting compliance requirements for data protection. NSGs enforce network segmentation and access control, preventing unauthorized network access to critical resources. This comprehensive strategy reflects best professional practice by proactively mitigating identified risks through the strategic application of OCI's native security features, ensuring a secure and compliant cloud environment. Incorrect approaches analysis. An approach that relies solely on default security configurations without customization fails to address the specific risks identified in the matrix. Default settings are often too permissive and do not adhere to the principle of least privilege, creating potential vulnerabilities. This is a regulatory and ethical failure, as it demonstrates a lack of due diligence in protecting sensitive data and could lead to non-compliance with data protection regulations. Another incorrect approach might involve implementing security controls only after a security incident has occurred. This reactive strategy is a significant professional and ethical failure. It indicates a disregard for proactive risk management and places the organization at high risk of data breaches, reputational damage, and regulatory penalties. Best professional practice mandates a proactive security posture. Finally, an approach that prioritizes speed of deployment over security considerations, such as disabling security features to simplify setup or using insecure third-party tools without proper vetting, is also professionally unacceptable. This demonstrates a failure to understand the critical importance of security in cloud architecture and can lead to severe compliance violations and data compromise. Professional reasoning. Professionals should approach cloud architecture design by first conducting a comprehensive risk assessment, as indicated by the risk matrix. This assessment should then inform the selection and configuration of OCI services. The decision-making process should prioritize native OCI security services that offer granular control and robust protection. Architects must continuously evaluate the security posture of their deployments, staying updated on OCI's evolving security features and relevant compliance standards. A layered security approach, incorporating identity management, data encryption, and network security, is essential. When faced with competing demands for speed and security, architects must advocate for security best practices, educating stakeholders on the potential consequences of neglecting them and proposing solutions that balance both objectives effectively. Question 10. Governance review demonstrates that a financial services organization is migrating sensitive customer data to Oracle Cloud infrastructure. The organization needs to ensure this data is protected at rest and in transit, and that key management practices meet stringent regulatory compliance standards. Which of the following approaches best aligns with OCI best practices and regulatory expectations for securing sensitive data in the cloud? Option A. Utilize a third-party encryption tool that requires manual key management and is not integrated with OCI's native security services. Option B. Store encryption keys in plain text within a publicly accessible object storage bucket for easy retrieval by authorized applications. Option C. Implement transparent data encryption, TDE, for databases and utilize OCI object storage encryption at rest, with encryption keys managed by OCI Key Management Service, KMS. Option D. Encrypt all sensitive data at the application layer using custom encryption algorithms and store encryption keys within application configuration files. The correct answer is C. Implement transparent data encryption, TDE, for databases and utilize OCI object storage encryption at rest, with encryption keys managed by OCI Key Management Service, KMS. Explanation: scenario analysis. This scenario presents a common challenge in cloud environments where sensitive data is processed. The professional must balance the need for robust security with operational efficiency and cost-effectiveness. The core challenge lies in selecting the most appropriate data encryption strategy within the Oracle Cloud Infrastructure (OSI) ecosystem, considering the specific regulatory compliance requirements that are implicitly assumed for a certified associate exam. The complexity arises from understanding the different encryption options available in OCI, their implications for key management, and how they align with potential compliance mandates, e.g., data residency, access control, auditability. A misstep can lead to security vulnerabilities, compliance violations, or unnecessary operational overhead. Correct approach analysis. The correct approach involves leveraging OCI's native encryption capabilities, specifically transparent data encryption, TDE, for databases and encryption at rest for object storage, managed by OCI Key Management Service, KMS. This is best professional practice because it integrates seamlessly with OCI services, offering a managed and secure solution for key rotation, access control, and auditing. OCI KMS provides a centralized and highly available service for managing encryption keys, which is crucial for maintaining compliance with data protection regulations that often mandate strong key management practices, including regular key rotation and strict access policies. This approach ensures that data is encrypted both in transit and at rest without requiring significant application-level modifications, thereby reducing complexity and potential for error. It aligns with the principle of least privilege by allowing granular control over key access. Incorrect approaches analysis. One incorrect approach is to rely solely on client-side encryption implemented within applications without leveraging OCI's native encryption services. This is professionally unacceptable because it shifts the burden of key management entirely to the application developers, increasing the risk of insecure key storage, inconsistent implementation, and difficulties in auditing key usage across the entire cloud deployment. It also bypasses OCI's integrated security features, potentially leading to compliance gaps. Another incorrect approach is to store encryption keys in plain text within application configuration files or object storage buckets. This is a severe security and ethical failure. It directly violates fundamental security principles and regulatory requirements for protecting sensitive data. Storing keys in plain text makes them easily discoverable by unauthorized parties, rendering all encryption efforts futile and exposing the organization to significant data breaches and legal repercussions. A third incorrect approach is to use a third-party key management solution that is not integrated with OCI services and lacks robust auditing capabilities. While third-party solutions can be effective, an unintegrated solution can create operational silos, increase complexity in managing encryption across different environments, and make it challenging to demonstrate compliance with OCI-specific security controls and audit trails required by many regulatory frameworks. This can lead to a fragmented security posture and potential compliance issues. Professional reasoning. Professionals should adopt a decision-making framework that prioritizes security, compliance, and operational efficiency. This involves 1. Understanding the data's sensitivity and regulatory requirements. Identify what data is being stored and processed and what compliance standards e.g., GDPR, HIPAA, PCI DSS, if applicable to the exam's assumed jurisdiction, apply. 2. Evaluating OCI's native security features. Assess how OCI services like TDE, encryption at rest, and OCI KMS can meet these requirements. 3. Considering key management strategy. Determine the most secure and manageable approach for generating, storing, rotating, and revoking encryption keys. 4. Assessing operational impact. Evaluate the complexity of implementation, ongoing management, and potential performance implications of different encryption strategies. 5. Prioritizing integration and auditability. Favor solutions that integrate well with the OCI ecosystem and provide comprehensive audit logs for security and compliance verification. Question 11. Consider a scenario where a financial services company is deploying a new customer-facing web application on Oracle Cloud Infrastructure. This application processes sensitive customer financial data and must comply with strict regulatory requirements for data protection and access control. The application consists of multiple tiers: a public-facing web server, an application server, and a database server. The architecture utilizes a single virtual cloud network, VCN, with 3 distinct subnets for each tier. The company requires a robust security posture that minimizes the attack surface while ensuring the application remains accessible to legitimate users. Which approach best addresses the security requirements for controlling traffic between these application tiers and from the internet to the web tier? Option A. Implement network security groups, NSG, to define granular ingress and egress rules for the network interfaces of the web, application, and database servers, allowing only necessary traffic between tiers and from the internet to the web tier. Option B. Disable all security list and network security group rules for the application subnets, assuming that the application itself is hardened and no external network threats are anticipated. Option C. Utilize only security lists to manage all traffic control, creating very permissive rules for each subnet to ensure connectivity, and assume that the sensitive data is adequately protected by encryption. Option D. Configure broad ingress rules in the security list associated with the VCN to allow all traffic from the internet to the web subnet, and then rely on application-level firewalls for internal tier communication. Correct answer is A. Implement network security groups, NSG, to define granular ingress and egress rules for the network interfaces of the web, application, and database servers, allowing only necessary traffic between tiers and from the internet to the web tier. Explanation. This scenario presents a common challenge in cloud architecture: balancing security posture with application performance and accessibility requirements, particularly when dealing with sensitive data and compliance mandates. The professional challenge lies in selecting the most appropriate network security controls within Oracle Cloud Infrastructure, OSI, to meet these competing demands effectively and efficiently, while adhering to the principles of least privilege and defense in depth. The correct approach leverages network security groups, NSG, for granular, application-centric security policy enforcement at the instance level. This aligns with best practices for OCI networking by allowing security rules to be associated directly with the network interfaces of specific compute resources. This provides a more dynamic and manageable security model compared to security lists, especially in environments with frequently changing instance deployments or complex application dependencies. NSGs enable security policies to follow the workload, simplifying management and reducing the risk of misconfiguration. This approach is professionally sound, as it directly addresses the need for fine-grained control over traffic to and from the application servers hosting sensitive data, ensuring that only necessary ports and protocols are open, thereby minimizing the attack surface. It also supports the principle of least privilege by allowing specific rules to be applied to the application instances themselves, rather than broader subnet-level rules. An incorrect approach would be to rely solely on security lists for all ingress and egress traffic filtering. While security lists are fundamental for VCN-level security, using them exclusively for application-specific rules can lead to overly broad policies. This increases the risk of unintended access and makes it harder to audit and manage security for individual applications, especially in larger deployments. This approach fails to implement defense in depth effectively at the instance level and can violate the principle of least privilege by exposing more ports than necessary to the subnet. Another incorrect approach would be to configure overly permissive rules in either security lists or NSGs, such as allowing all ingress traffic on all ports from any source. This is a significant security failure, directly contravening the principle of least privilege and creating a wide-open attack vector. Such a configuration would be professionally unacceptable and could lead to severe data breaches and regulatory noncompliance, as it demonstrates a lack of due diligence in protecting sensitive data. A further incorrect approach would be to disable all security list and NSG rules, assuming that other security measures, like application-level firewalls, are sufficient. This is a critical oversight. While application-level security is important, network-level controls like security lists and NSGs provide an essential layer of defense in depth. Relying solely on application security without robust network controls leaves the application vulnerable to network-based attacks that could bypass application-level protections. This demonstrates a misunderstanding of foundational cloud security principles. The professional decision-making process for such situations involves a thorough understanding of the application's traffic patterns, data sensitivity, and compliance requirements. Architects must first identify the specific network endpoints and protocols required for the application to function correctly. Then, they should apply the principle of least privilege, allowing only the necessary traffic. Defense in depth should be implemented by utilizing multiple layers of security, including VCN-level controls, security lists, and instance-level controls, NSG. NSGs are generally preferred for application-specific rules due to their granular nature and ability to follow workloads. Regular review and auditing of security rules are also crucial to maintain an effective security posture. Question 12. The investigation demonstrates that a cloud-native application handling sensitive customer data is experiencing frequent deployments to meet market demands. However, concerns have been raised about potential security vulnerabilities being introduced during this rapid release cycle. The architecture team is evaluating different strategies to ensure the application remains secure and compliant without significantly hindering the deployment velocity. Which of the following approaches best addresses this challenge while adhering to best practices for cloud-native security and compliance? Option A. Conduct comprehensive manual security reviews of the application code and infrastructure only after each deployment is completed. Option B. Disable security logging and auditing features to maximize application performance and reduce operational overhead. Option C. Focus security efforts on implementing robust network firewalls and intrusion detection systems at the application's network perimeter. Option D. Integrate automated security scanning tools, policy enforcement, and least privilege access controls directly into the CI/CD pipeline. The correct answer is D. Integrate automated security scanning tools, policy enforcement, and least privilege access controls directly into the CI/CD pipeline. Explanation: Scenario analysis. This scenario presents a common challenge in cloud-native application development, balancing rapid innovation with robust security and compliance requirements. The need to deploy frequently, a hallmark of cloud-native, can inadvertently introduce vulnerabilities if not managed with strict governance. The professional challenge lies in selecting an approach that enables agility without compromising the integrity and security of sensitive data, which is paramount in regulated industries. The architect must consider the implications of each choice on operational efficiency, security posture, and adherence to industry best practices for cloud deployments. Correct approach analysis. Implementing a comprehensive DevSecOps pipeline that integrates security scanning, automated policy enforcement, and least privilege access controls into the CI/CD workflow represents best professional practice. This approach embeds security throughout the development lifecycle, aligning with the principle of security by design. For cloud-native applications, this is crucial for maintaining compliance with data protection regulations and industry standards. By automating security checks and controls, it ensures that every deployment adheres to predefined security policies, minimizing the risk of introducing vulnerabilities and maintaining an auditable trail of security configurations, which is often a regulatory requirement. This proactive stance is essential for building trust and ensuring the ongoing security and compliance of the application. Incorrect approach is analysis. Relying solely on manual security reviews after deployment introduces significant risk. This approach is reactive rather than proactive, meaning vulnerabilities could be exploited before they are identified. From a regulatory perspective, this can lead to non-compliance with data breach notification laws and security standards that mandate timely detection and remediation of threats. It also creates an unacceptable delay in the feedback loop for developers, hindering the agility expected from cloud-native architectures. Implementing security measures only at the network perimeter, such as firewalls and intrusion detection systems, is insufficient for cloud-native applications. While important, these measures do not address vulnerabilities within the application code itself or within the containerized environments. Modern cloud-native applications often have distributed architectures and microservices, making a perimeter-only security model porous and ineffective against sophisticated attacks. Regulatory frameworks increasingly expect layered security, including application-level security and data encryption, which this approach neglects. Disabling security logging and auditing to improve application performance is a severe ethical and regulatory failure. Security logs are critical for incident response, forensic analysis, and demonstrating compliance with audit requirements. Disabling them not only obstructs the ability to detect and respond to security incidents, but also makes it impossible to prove adherence to security policies and regulation. This directly violates principles of accountability and transparency, which are fundamental to professional conduct and regulatory compliance. Professional reasoning. Professionals should adopt a risk-based approach, prioritizing solutions that embed security and compliance from the outset. This involves understanding the specific regulatory landscape applicable to the data being handled and the industry sector. The decision-making process should involve evaluating each potential solution against these requirements, considering its impact on agility, scalability, and operational overhead. A key consideration is the automation of security controls and the establishment of clear governance policies that are enforced throughout the application lifecycle. Continuous monitoring and adaptation are also vital, ensuring that security and compliance remain robust as the application evolves. Question 13. Upon reviewing the requirements for deploying a new microservices-based application on Oracle Cloud infrastructure, which utilizes Docker containers for packaging and requires robust orchestration, security, and scalability, what is the most appropriate architectural decision to ensure efficient management and adherence to best practices? Option A. Setting up and managing a self-hosted Kubernetes cluster on OCI compute instances. Option B. Deploying the application using Oracle Container Engine for Kubernetes OAK to leverage a managed Kubernetes service. Option C. Utilizing Oracle functions for serverless container execution without explicit orchestration. Option D. Deploying Docker containers directly onto OCI compute instances without an orchestration platform. The correct answer is B. Deploying the application using Oracle Container Engine for Kubernetes OAK to leverage a managed Kubernetes service. Explanation. This scenario presents a common challenge in cloud architecture, balancing the benefits of containerization with the need for robust security and compliance. The professional architect must consider not only the technical advantages of Docker and Kubernetes, but also how their implementation aligns with Oracle Cloud Infrastructure's best practices and any relevant, though not explicitly stated for this exam scope, industry standards for data handling and application deployment. The challenge lies in selecting a deployment strategy that is both efficient and secure, minimizing potential attack vectors and ensuring data integrity. The correct approach represents best professional practice because it leverages OCI's managed Kubernetes service, Oracle Container Engine for Kubernetes OAK. OKE abstracts away much of the underlying infrastructure management, allowing the architect to focus on application deployment and security configurations. By using OKE, the organization benefits from Oracle's built-in security features, automated patching, and integration with other OCI services like Identity and Access Management (IAM) and Virtual Cloud Network (VCN). This managed service approach inherently reduces the operational burden and the risk of misconfiguration, which are critical for maintaining a secure and compliant environment. It aligns with the principle of least privilege and defense in depth by allowing granular control over network access and pod security policies. An incorrect approach involving self-managed Kubernetes on OCI compute instances would be professionally unacceptable due to significant regulatory and ethical failures. This approach places the entire burden of Kubernetes cluster management, including security patching, network configuration, and access control, onto the organization. This significantly increases the risk of vulnerabilities and misconfigurations that could lead to data breaches or unauthorized access, violating implicit ethical obligations to protect customer data and potentially contravening general principles of due diligence in system security. Furthermore, it would likely lead to increased operational costs and complexity, diverting resources from core business functions. Another incorrect approach, deploying containers directly onto OCI compute instances without a container orchestration platform, bypasses the benefits of containerization management and scalability. This would result in a highly manual and error-prone deployment process, making it difficult to manage, update, and scale applications effectively. It also introduces security risks by not leveraging the built-in security features and best practices associated with orchestrated container environments. This lack of structured management and security oversight would be a failure in professional responsibility to implement robust and maintainable solutions. The professional reasoning framework for this situation involves a systematic evaluation of OCI services against the project's technical requirements, security mandates, and operational capabilities. The architect should first identify the core problem, deploying containerized applications, and then explore OCI's offerings that address this. A key step is to prioritize managed services where available, as they typically incorporate built-in security and compliance features and reduce the operational overhead. The decision should be guided by a risk assessment, considering the potential impact of security vulnerabilities and the cost-benefit analysis of different deployment models. Finally, the chosen solution must be validated against OCI best practices for security and performance. Question 14. The performance metrics show consistently slow boot times for several critical applications hosted on Oracle Cloud infrastructure. The current boot volumes are configured with standard block storage. What is the most appropriate architectural approach to address this performance bottleneck while ensuring application availability and adherence to OCI best practices? Option A. Migrate the boot volumes to object storage to reduce costs and improve data durability for the operating system. Option B. Reconfigure the existing standard block storage boot volumes with a higher redundancy setting to enhance data protection during the boot process. Option C. Evaluate and potentially migrate critical application boot volumes to NVMe-based boot volumes to leverage their superior IOPS and throughput for faster boot operations. Option D. Increase the size of the existing standard block storage boot volumes to accommodate potential future growth and improve overall system responsiveness. The correct answer is C. Evaluate and potentially migrate critical application boot volumes to NVMe-based boot volumes to leverage their superior IOPS and throughput for faster boot operations. Explanation. Scenario analysis. The scenario presents a common challenge in cloud architecture, balancing performance requirements with cost-effectiveness and data durability. The performance metrics indicating slow boot times for critical applications necessitate immediate attention, but the underlying cause could stem from various factors related to boot volume configuration and storage. A hasty decision without proper risk assessment could lead to suboptimal resource allocation, increased operational costs, or even data loss if not handled correctly. The professional challenge lies in identifying the root cause and selecting the most appropriate solution that aligns with business objectives and OCI best practices. Correct approach analysis. The correct approach involves a thorough investigation into the boot volume's performance characteristics and the underlying storage. This includes understanding the IOPS and throughput capabilities of the chosen boot volume type and its associated storage. For critical applications requiring fast boot times, selecting a boot volume type that offers higher performance, such as NVMe-based boot volumes, is a best practice. This directly addresses the observed performance bottleneck by providing faster data access during the boot process. This approach is professionally sound as it prioritizes application availability and performance, which are key business drivers, while also considering the technical implications of storage choices. It aligns with the principle of selecting appropriate services for specific workloads to ensure optimal outcomes. Incorrect approaches analysis. Choosing a boot volume with lower performance characteristics to reduce costs without a thorough analysis of the performance impact is a regulatory and ethical failure. It prioritizes cost savings over application functionality and user experience, potentially violating service-level agreements, SLAs, and leading to business disruption. This demonstrates a lack of due diligence in understanding workload requirements. Migrating the boot volume to a different storage tier without understanding the specific performance needs of the operating system and applications during boot is also professionally unsound. While some storage tiers offer higher durability or lower costs, they might not provide the necessary IOPS or throughput for rapid boot sequences, thus exacerbating the problem or introducing new performance issues. This approach lacks a data-driven decision-making process. Simply increasing the size of the existing boot volume without considering its performance tier is an ineffective solution. Boot volume performance is primarily determined by its type and the underlying storage technology, not just its capacity. This approach wastes resources and fails to address the root cause of the slow boot times, representing a failure in technical problem solving and resource management. Professional reasoning. Professionals should adopt a structured approach to troubleshooting and architectural decisions. This involves 1. Clearly defining the problem and its impact. 2. Gathering relevant data, performance metrics, application requirements. 3. Identifying potential causes and solutions. 4. Evaluating each solution against technical feasibility, performance impact, cost, and business objectives. 5. Implementing the chosen solution with proper testing and monitoring. This systematic process ensures that decisions are informed, justifiable, and aligned with best practices and organizational goals. Question 15. Examination of the data shows that a company is storing sensitive customer PII in Oracle Cloud Infrastructure object storage buckets. The company needs to allow its customer service application to retrieve this data for processing, but it must prevent any unauthorized access or modification. Which approach best ensures regulatory compliance and data security? Option A. Grant all authenticated users within the tenancy read-write access to all object storage buckets, including those containing PII, to simplify access management. Option B. Make the object storage buckets containing PII publicly accessible so that the customer service application can easily retrieve the data from any location. Option C. Implement strict network security lists at the VCN level to block all external access to the object storage service, assuming this will protect the PII. Option D. Configure IAM policies to grant the customer service application service principal read-only access to the specific object storage buckets containing PII, while ensuring all other users and services have no access to these buckets, unless explicitly granted. Correct answer is D. Configure IAM policies to grant the customer service application service principal read-only access to the specific object storage buckets containing PII, while ensuring all other users and services have no access to these buckets unless explicitly granted. Explanation. Scenario analysis. This scenario presents a common challenge in cloud environments, balancing data accessibility for legitimate business operations with the imperative to protect sensitive information from unauthorized access. The challenge lies in implementing granular access controls that align with regulatory requirements and internal security policies, especially when dealing with potentially sensitive customer data stored in object storage. Misconfigurations can lead to significant security breaches, regulatory penalties, and reputational damage. Correct approach analysis. The correct approach involves leveraging Oracle Cloud Infrastructure's identity and access management (IAM) policies to enforce the principle of least privilege. This means granting only the necessary permissions to users and services that interact with the object storage buckets. Specifically, using IAM policies to define granular access at the bucket level, allowing read-only access for specific user groups or applications, while restricting write or delete operations, is crucial. This aligns with best practices for data security and is a fundamental requirement for many compliance frameworks that mandate data protection and access control. By ensuring that only authorized entities can access or modify data, this approach directly addresses the risk of data exfiltration or unauthorized modification, thereby upholding regulatory obligations related to data privacy and security. Incorrect approach is analysis. Making object storage buckets publicly accessible without proper authentication and authorization is a severe regulatory and ethical failure. This directly violates data protection principles and exposes sensitive data to the public internet, leading to potential data breaches and non-compliance with regulations like GDPR or CCPA, depending on the jurisdiction implied by the exam's focus, which is US-centric for OCI certifications unless otherwise specified. Granting overly broad permissions, such as allowing all authenticated users within the tenancy to have read-write access to all object storage buckets, is another failure. This violates the principle of least privilege, increasing the attack surface and the risk of accidental data deletion or unauthorized modification by internal actors. It fails to implement necessary controls for sensitive data, making it difficult to audit access and demonstrate compliance. Relying solely on network security controls like VCN security lists or network ACLs to protect object storage data is insufficient. While these controls protect network traffic, they do not provide granular control over who can access specific objects or buckets within object storage itself. Object storage security is primarily managed through IAM policies, and neglecting this layer leaves data vulnerable even if network access is restricted. This approach fails to address the core access control mechanisms required for data security and regulatory adherence. Professional reasoning. Professionals must adopt a defense-in-depth strategy for cloud security. This involves understanding the specific data being stored, its sensitivity, and the relevant regulatory requirements. The decision-making process should prioritize implementing granular access controls using IAM policies, adhering to the principle of least privilege. Regular auditing of access logs and policy reviews are essential to maintain a secure posture and ensure ongoing compliance. When in doubt, always err on the side of stricter access controls, and gradually loosen them only after thorough risk assessment and justification. Question 16. Performance analysis shows that a growing enterprise is experiencing fluctuating but generally increasing resource utilization across its Oracle Cloud Infrastructure (OSI) environment. The finance department requires a predictable monthly expenditure for cloud services, while the engineering team needs the flexibility to scale resources up or down based on dynamic business demands. Given these competing requirements, which OCI pricing model strategy best balances cost predictability with operational agility for this enterprise? Option A. Maintaining a pure pay-as-you-go model to ensure maximum flexibility, accepting the higher per-unit cost for the benefit of not having any upfront commitment. Option B. Transitioning to a universal credits model with a commitment level that aligns with the projected average monthly spend, allowing for discounts while retaining flexibility to consume credits across various OCI services. Option C. Committing to a fixed number of universal credits that precisely matches the highest anticipated monthly peak usage, even if this leads to significant underutilization during off-peak periods. Option D. Implementing a custom pricing agreement with Oracle that guarantees a fixed monthly cost for a specific set of services, regardless of actual consumption. The correct answer is B. Transitioning to a universal credits model with a commitment level that aligns with the projected average monthly spend, allowing for discounts while retaining flexibility to consume credits across various OCI services. Explanation. This scenario presents a common challenge for cloud architects, optimizing cloud spend while ensuring predictable budgeting and leveraging potential cost savings. The professional challenge lies in accurately forecasting resource consumption and aligning it with the most advantageous pricing model offered by Oracle Cloud Infrastructure (OSI). Misjudging the consumption patterns can lead to unexpected costs or missed opportunities for discounts, impacting project profitability and stakeholder confidence. Careful judgment is required to balance flexibility with cost predictability. The correct approach represents best professional practice because it directly addresses the need for predictable budgeting and cost optimization by leveraging the benefits of universal credits. Universal credits provide a commitment to a certain spend level, which in turn unlocks significant discounts and a more predictable cost structure compared to the pure pay-as-you-go model. This aligns with professional responsibility to manage resources efficiently and provide accurate financial forecasts to stakeholders. It demonstrates a proactive approach to cost management, moving beyond reactive spending to strategic financial planning within the OCI framework. An incorrect approach that focuses solely on the immediate flexibility of pay-as-you-go without considering the long-term cost implications fails to meet professional standards for cost management. Pay-as-you-go offers agility. It lacks the built-in discount structures available with committed spend. This can lead to higher overall costs for sustained workloads, potentially violating ethical obligations to deliver value and manage client or organizational funds responsibly. Another incorrect approach that attempts to apply a universal credits commitment without a thorough understanding of the workload's actual consumption patterns is also professionally unsound. This could lead to overcommitment, where the organization pays for credits that are not fully utilized, resulting in wasted expenditure. This demonstrates a lack of due diligence and can lead to financial inefficiencies, undermining professional credibility. The professional reasoning process for similar situations should involve a detailed analysis of current and projected resource utilization, understanding the specific discount tiers and benefits associated with different OCI pricing models, and engaging with stakeholders to align financial expectations with technical implementation. A phased approach, perhaps starting with pay-as-you-go for initial exploration, and then transitioning to universal credits as consumption patterns stabilize and become predictable, is often a prudent strategy. This iterative process ensures that the chosen pricing model best serves both the technical requirements and the financial objectives. Question 17. Strategic planning requires a cloud architect to provision Oracle Cloud Infrastructure block volumes for a new customer-facing application. The application is expected to have moderate but consistent read and write operations, with occasional bursts of higher activity during peak usage hours. The primary goal is to ensure a responsive user experience while managing operational costs effectively. Which approach best aligns with these requirements? Option A. Provision block volumes using the ultra-high performance tier to guarantee the highest possible responsiveness for all user interactions, regardless of cost. Option B. Provision block volumes using the balanced performance tier, as it offers a good balance between cost and performance suitable for general-purpose workloads with variable I/O patterns. Option C. Provision block volumes using the high-performance tier, as it provides a significant performance uplift over balanced, ensuring no user will experience any latency. Option D. Provision block volumes using the lower-cost performance tier, assuming that most operations will be light and the cost savings are paramount. The correct answer is B. Provision block volumes using the balanced performance tier, as it offers a good balance between cost and performance suitable for general-purpose workloads with variable I/O patterns. Explanation. Scenario analysis. This scenario presents a common challenge in cloud architecture, balancing performance needs with cost efficiency for data storage. The professional must understand the nuances of Oracle Cloud Infrastructure, OCI, block volume performance tiers, and their implications for application responsiveness and operational expenditure. The challenge lies in accurately mapping application I/O patterns to the most suitable and cost-effective performance tier without compromising critical business functions. Misjudging these requirements can lead to either overspending on unnecessary performance or under-provisioning, resulting in application slowdowns and user dissatisfaction. Correct approach analysis. The correct approach involves a thorough assessment of the application's I/O characteristics, including its IOPS, input/output operations per second, and throughput requirements, and then selecting the OCI block volume performance tier that best matches these needs. This aligns with best professional practice by prioritizing a data-driven decision based on technical requirements and cost optimization. For the Oracle Cloud Infrastructure 2023 Certified Architect Associate exam, this demonstrates an understanding of OCI's service offerings and the ability to apply them effectively to solve business problems. There are no specific regulatory mandates directly dictating block volume tier selection in the U.S. context for this exam, but the ethical consideration is to provide a solution that is both technically sound and economically responsible for the client. Incorrect approaches analysis. Choosing the highest performance tier, ultra-high performance, without a clear need is a failure of cost management and resource optimization. While it guarantees performance, it incurs unnecessary expense, which is professionally irresponsible when a lower tier would suffice. This could be seen as a failure to act in the client's best financial interest. Selecting the lowest performance tier, lower cost, without verifying if it meets the application's minimum IOPS and throughput requirements is a significant risk. This could lead to application performance degradation, impacting user experience and potentially business operation. This represents a failure to adequately assess technical requirements and a disregard for the potential negative business impact, which is ethically questionable. Opting for a mid-tier performance level without understanding the specific I/O patterns of the application is a guess. While it might be a reasonable starting point, it lacks the rigor of a performance-based decision. This approach demonstrates a lack of deep analysis and could lead to either overspending or underperformance, neither of which is ideal professional practice. Professional reasoning. Professionals should approach such decisions by first gathering detailed performance metrics of the application in its current environment or through testing. This data should then be used to map against the defined performance characteristics of OCI block volume tiers. A phased approach, starting with a tier that closely matches the assessed needs, and then monitoring performance and cost, allows for adjustments. This iterative process ensures that the chosen tier is optimal for both performance and cost, reflecting a commitment to delivering value and maintaining system integrity. Question 18. Analysis of a financial services firm operating under strict data residency laws, which mandate that all customer financial transaction data must reside within the country's borders, is considering its cloud deployment strategy. The firm aims to enhance its agility and reduce operational costs, which deployment model best aligns with both regulatory compliance and business objectives. Option A. A hybrid cloud model, where sensitive financial data is hosted on a private cloud infrastructure within the country, and less sensitive customer analytics workloads are run on a public cloud. Option B. A multi-cloud strategy exclusively using public cloud providers located in different geographical regions for all operations. Option C. A purely private cloud deployment hosted entirely on premises within the firm's own data centers, with no external cloud services utilized. Option D. A public cloud-only model, relying on a single global public cloud provider for all its services. The correct answer is A. A hybrid cloud model, where sensitive financial data is hosted on a private cloud infrastructure within the country, and less sensitive customer analytics workloads are run on a public cloud. Explanation. This scenario presents a professional challenge due to the critical need to balance business agility with stringent regulatory compliance, particularly concerning data sovereignty and security. The organization operates within a jurisdiction that mandates specific data handling and residency requirements for financial services data. Choosing the wrong deployment model could lead to significant legal penalties, reputational damage, and operational disruptions. The correct approach involves a hybrid cloud deployment. This is best professional practice because it allows the organization to leverage the scalability and cost efficiency of a public cloud for non-sensitive workloads, while keeping highly regulated financial data within a private cloud environment that is fully controlled and compliant with local data residency laws. This model offers a pragmatic balance, enabling innovation and agility without compromising regulatory adherence. It demonstrates a mature understanding of risk management and compliance obligations. An incorrect approach would be to solely utilize a public cloud for all financial services data. This fails to meet the regulatory requirement for data residency and could expose the organization to breaches of data sovereignty laws. Ethically, this demonstrates a disregard for customer privacy and legal obligations. Another incorrect approach is to maintain an entirely on-premises private cloud without any cloud integration. While compliant, this approach sacrifices the benefits of cloud computing, such as scalability, disaster recovery, and cost optimization, leading to potential competitive disadvantages and increased operational overhead. This can be seen as a failure to adopt best practices for modern IT infrastructure. Professionals should approach such decisions by first thoroughly understanding the regulatory landscape and its specific implications for data handling. This involves identifying which data types are subject to specific regulations. Subsequently, they must assess the capabilities and limitations of different deployment models against these requirements and business objectives. A risk-based approach, prioritizing compliance and security for sensitive data while optimizing for cost and agility for less sensitive data, is crucial. This involves engaging with legal and compliance teams early in the decision-making process. Question 19. Benchmark analysis indicates that an organization is migrating a critical web application and its associated database to Oracle Cloud Infrastructure, OSI. The web application needs to be accessible from the internet, while the database should only be accessible from the web application's compute instances. The organization wants to implement a robust network security strategy that protects against common web exploits and ensures granular control over network traffic. Which of the following approaches best meets these requirements while adhering to OCI best practices for network security? Option A. Deploy OCI Web Application Firewall, WAF, for the web application and use OCI Security List to manage access to the database from the web application instances. Option B. Implement OCI Web Application Firewall, WAF, to protect the web application and use OCI Network Security Groups, NSG, to control traffic between the web application instances and the database. Option C. Rely solely on OCI Network Security Groups, NSG, to filter all inbound and outbound traffic for both the web application and the database. Option D. Utilize only OCI security lists to enforce all network access controls for both the web application and the database. Correct answer is B. Implement OCI Web Application Firewall (WAF) to protect the web application and use OCI Network Security Groups (NSG) to control traffic between the web application instances and the database. Explanation: Scenario analysis. This scenario presents a common challenge in cloud security, balancing granular network access control with operational efficiency and cost-effectiveness. The organization needs to secure its OCI environment against external threats, while ensuring legitimate internal and external services can communicate. The challenge lies in selecting a firewalling strategy that is both robust and manageable, avoiding overly restrictive policies that hinder operations or overly permissive ones that create vulnerabilities. The need to comply with OCI best practices and potentially industry-specific regulations, though not explicitly stated, implied by a professional context, adds another layer of complexity. Correct approach analysis. Implementing OCI Network Security Groups (NSG) for granular control at the instance level, combined with OCI Web Application Firewalls (WAF) for Layer 7 protection of web applications, represents best professional practice. NSGs provide stateful firewall rules that are associated directly with VNIC, offering precise control over inbound and outbound traffic for individual compute instances or groups of instances. This aligns with the principle of least privilege, ensuring that only necessary ports and protocols are open. OCI WAF complements this by providing specialized protection against common web exploits like SQL injection and cross-site scripting, operating at the application layer where NSGs are less effective. This layered security approach is a recognized industry standard for cloud environments, offering comprehensive protection. Incorrect approach is analysis. Relying solely on OCI Network Security Groups (NSG) for all network traffic, including Layer 7 web application traffic, is an incomplete approach. While NSGs are powerful for network-level control, they lack the application-aware capabilities to inspect and filter malicious HTTP/S traffic effectively. This leaves web applications vulnerable to sophisticated attacks that NSGs are not designed to mitigate, representing a significant security gap and a failure to implement a comprehensive defense-in-depth strategy. Implementing only OCI Web Application Firewalls (WAF) without NSGs is also insufficient. WAFs are specialized for web applications and do not provide general network-level filtering for other types of traffic, e.g., SSH, database connections. This would leave non-web services exposed to network-level threats and unauthorized access, violating the principle of securing all network interfaces and protocols. Using only OCI security lists for all network security is a less granular and less efficient approach compared to NSGs. Security lists operate at the subnet level, applying rules to all VNIC within that subnet. While they offer basic firewalling, they lack the instance-level specificity of NSGs, making it harder to implement the principle of least privilege for individual resources. This can lead to overly permissive rules that increase the attack surface and make troubleshooting more complex, representing a less secure and less manageable configuration. Professional reasoning. Professionals should adopt a defense-in-depth strategy, layering security controls to address different threat vectors. This involves understanding the capabilities of each OCI security service and applying them appropriately. For network security, NSGs provide essential instance-level control. For web applications, WAF offers specialized protection. Security lists can be used for broader subnet-level policies, where granular control is not as critical. The decision-making process should prioritize least privilege, operational requirements, and the specific threat landscape of the applications and services being deployed. Regularly reviewing and updating firewall rules based on security best practices and observed traffic patterns is also crucial. Question 20. The control framework reveals that a new application needs to be deployed rapidly on Oracle Cloud Infrastructure, OSI. The development team is eager to start coding, but the architect is concerned about ensuring a secure and compliant deployment. Which approach best addresses the architect's concerns while facilitating efficient application delivery within the OCI 2023 Certified Architect Associate scope? Option A. Assume OCI handles all security aspects by default and focus solely on application-level security features provided by the development framework. Option B. Rely entirely on the development team's existing knowledge of other cloud platforms to design the OCI architecture, without specific investigation into OCI's unique offerings and operational paradigms. Option C. Conduct a comprehensive review of OCI's global infrastructure, core services, compute, storage, networking, identity and access management, and the shared responsibility model before commencing detailed application architecture design. Option D. Prioritize immediate application coding and defer any deep dives into OCI's specific services and the shared responsibility model until after the initial deployment. The correct answer is D. Prioritize immediate application coding and defer any deep dives into OCI's specific services and the shared responsibility model until after the initial deployment. Explanation. Scenario analysis. This scenario presents a common challenge in cloud adoption, balancing the need for rapid deployment with robust security and compliance. The pressure to deliver a new application quickly can lead to shortcuts in understanding the foundational aspects of the cloud environment, specifically OCI's shared responsibility model and its core services. A failure to grasp these fundamentals can result in misconfigurations, security vulnerabilities, and non-compliance with potential regulatory requirements, even if not explicitly stated in the exam's jurisdiction. The principle of due diligence applies universally. The professional challenge lies in prioritizing thorough understanding and adherence to best practices over expediency. Correct approach analysis. The correct approach emphasizes a foundational understanding of OCI's core services and the shared responsibility model. This aligns with best professional practice by ensuring that the architect has a comprehensive grasp of what OCI manages versus what the customer is responsible for. This knowledge is critical for designing secure, compliant, and cost-effective solutions. Specifically, understanding OCI's overview, including its global infrastructure, core compute, storage, and networking services, is a prerequisite for making informed architectural decisions. This proactive approach minimizes risks and ensures that the application is built on a solid, well-understood foundation, adhering to the implicit expectation of responsible cloud architecture design. Incorrect approaches analysis. Focusing solely on application development without understanding the underlying OCI infrastructure is a significant regulatory and ethical failure. It demonstrates a lack of due diligence and a disregard for the security and operational integrity of the deployed application. This can lead to breaches, data loss, and service disruptions, all of which have severe consequences. Neglecting the shared responsibility model, for instance, can result in security gaps where the customer assumes OCI handles certain security aspects that are, in fact, their responsibility, leading to non-compliance and potential legal repercussions. Similarly, ignoring OCI's service limits and best practices can lead to performance issues and unexpected costs, indicating poor architectural planning and a failure to act in the best interest of the project and its stakeholders. Professional reasoning. Professionals should adopt a phased approach to cloud adoption. This begins with a thorough understanding of the cloud provider's offerings, including their security posture, compliance certifications, and service capabilities. For diving into application development, architects must familiarize themselves with the OCI overview, focusing on how core services like compute, storage, networking, and identity and access management function. This foundational knowledge allows for informed decisions regarding resource provisioning, security configurations, and cost management. A continuous learning mindset is also crucial, as cloud technologies evolve rapidly. This systematic approach ensures that solutions are not only functional, but also secure, compliant, and aligned with business objectives.